Hello everyone. This is the second lecture of the sequential circuits. In the first lecture, we already discussed about the basics of the sequential circuits. What is the difference between combinational and sequential circuits? We already discussed this thing in previous lecture. We already discussed about the latch in the previous lecture. So in the second lecture, we will discuss about the flip-flop. What is the meaning of triggering? What is the difference between S triggering and the level triggering? Fine. And in this lecture, we will also discuss about the SR flip-flop, JK flip-flop, D flip-flop and other types of flip-flops. So in all these flip-flops, we will discuss about its truth table, characteristic table, excitation table and its representation and the state representation of the flip-flops. So first of all, what do you mean by the flip-flop and what is the difference between flip-flop and the latch? You know, flip-flop is basically the 1-bit storage circuit, fine, and in the latch there is no clock, while in the flip-flop clock is used. Basically we can say the usually latch with clock or the enable input is called the flip-flop. Okay, if we connect one clock in our previous Nand or NOR based latch circuit, then it becomes the flip-flop. Fine. So flip-flop may be S triggered or the level triggered. So this is the basic difference between flip-flop and the latch. Now we will study about the SR flip-flop. So SR flip-flop, the full form of SR flip-flop is set and the reset flip-flop. Fine. We already discussed that the flip-flop is basically the latch with the clock input. Fine. So here first we will design the SR flip-flop with the help of Nand latch. Then we will design the SR flip-flop with the help of the NOR latch. So first we will design the circuit diagram for this SR flip-flop. So we all know basically in the SR flip-flop, circuit diagram, one is our latch. Fine. So this is which latch? This is the Nand latch. Fine. So this is our latch. So if we connect in this SR flip-flop with one extra clock circuitry, then it converts to the flip-flop. Means the basic difference between flip-flop and latch is flip-flop is basically the maybe S triggered and the level triggered, while the latch is always the level triggered. So if we connect two more NAND gate here, one here, and these two NAND gates are controlled with the help of one input that is called the clock. And these two inputs, this is the S and this is R. So this is basically our clock circuitry. And this complete circuit is called our SR flip-flop. So here one term is used, that is clock. So what is clock? So clock is basically defined by like this. So this is the clock is the combination of ones and the zero. So this is the clock. So in this clock basically there are two things. One is the edge. So in this clock this is called the edge. Fine. And this is called the level of the clock. And based on this level and the edges, we are saying our flip-flop is level triggered or the edge triggered. Triggering means the to on the circuit. Means if we are saying our flip-flop is level triggered, means this flip-flop works only when at this level only. And we are saying the S triggered, then it means our flip-flop works at this edge. So further, this level triggered and the S triggered are categorized into two types. One is positive S level triggered, then the negative level triggered. And similarly, the S triggered, similarly the positive S triggered, then the negative S triggered. So this is the positive edge, means the positive edge means if the values goes from 0 to 1, then it is called the positive edge. If the value goes from 1 to 0, then this is called the negative edge. If our flip-flop or any circuit works at this positive edge at that time, or in that case, we are saying that our circuit is positive edge triggered. If our circuit works at this negative edge, then at that time we are saying our circuit is the negative edge triggered. Similarly, if our circuit works at the positive level, means the level 1, then we are saying the positive levels. And in the other clock, if our circuit works at this negative level, fine, then we are saying it is the negative edge triggered. So this is our negative level, fine. So this is the meaning of triggering, and this is the meaning of level triggered and the S triggered. So our flip-flop works both at the level triggered as well as the S triggered, while in case of latch, this is only the level triggered, fine. So here the output is Q and the Q bar, fine. So this is the complete circuit of the SR flip-flop. And in terms of block diagram, if we are saying in terms of block diagram, so block diagram is basically the combination of inputs and the output in the form of black box. So here there are basically three inputs. One is S, second one is R, and third one is clock. And the two outputs, one is Q and this is the Q bar, and this is the SR flip-flop. So if the clock is like this, simple this thing, then in that case this is called the positive level triggered, flip-flop, fine. And if this circuit or this block diagram is represented as like this, fine, then this is called the negative level triggered, fine. Similarly, in terms of for S triggered, we are representing this thing as like this. So we are representing this thing. We are representing in terms of S triggering. If the circuit is like this or the block diagram is like this, then it means this is the S triggered. So here this is the positive S triggered flip-flop, fine. And if we place a bubble here, then it becomes the negative S triggered. So now it becomes the negative S triggered. If you place a bubble here, it means it becomes the negative. If there is no bubble, then it means this is the positive S triggered. So this is the representation of level triggered flip-flop and the S triggered flip-flop. Now from this truth table or from this circuit, we will derive the truth table of this SR flip-flops. So the truth table is basically the representation of inputs and the outputs. So in this SR flip-flops, so basically there are three inputs. One is clock, second one is SR, and the output is Qn plus 1. So what is the meaning of Qn plus 1? So in the clock, before the clock, we are saying that is the present state and we are representing as the Qn. And after the clock, this present state is changed to the next state and we are representing the output as Qn plus 1. That's why in the truth table, we are presenting outputs at the next state, that is Qn plus 1. So in the combination, what happens if our clock is 0? If our clock is 0, the truth table of the NAND gate. So before the truth table of the NAND gate, in the NAND gate, there are basically 4 these combinations, and output is here the 1, 1, 1 and 0. This is the truth table of our NAND gate. So in this truth table, if you know any input is 0, then the output is 1. So here if the clock is 0, if any input becomes 0, then this output is basically, we are saying, if this clock is here, I am saying this is 0, this is 0. So in that case, the output becomes here the 1 and the 1. This 1 comes independent of S and R. So here we represent this as the, S and R as the don't care condition. Fine. So if it becomes 1, then what happened? It becomes 1 and 1. If the two inputs, this becomes 1 and the 1. So in the NAND based latch, if both inputs S and R becomes 1 and 1, then what is the output? So basically our output is the previous outputs. We already discussed this thing in the previous lecture. So this becomes the QN. Fine. So QN. So this state is called the memory state. Why it is called the memory state? Because in this, when the clock is 0, so output that is Qn plus 1 retains its previous value. So that's why it stores that previous value in that particular interval. So that's why it is called the memory here. Fine. So what happens if the clock is 1 here? What happens in this case? Then the value of, if it is 1, then the value depends on the S and R. Fine. So the output of this, both these NAND gates, depends on this input value S and R. So in the first combinations, we are saying both S is 0 and R is 0. So what is the value in that case? So if both S is 0, R is 0, so if I am saying S is 0, R is 0. So what is the value in that case here? If the input of the NAND gate is 0 and the 1, so the output is always 1. Here also output is always 1. Fine. And if the both inputs of the NAND latch is 1 and 1, then it depends. So the output depends, or the output store its previous value. Fine. And that is, we are saying the memory. Fine. So in the next state, if we are saying, or the next combination, we are saying clock is 1, and what is the combination here? S is 0, R is 1. Fine. So what happened here? If S is 0, in the next case S is 0, R is 1. So what happened in this case? The output here, if the both 1 is 0, 1 is 1. So here becomes 1. Fine. And here becomes 1 and 1. So here becomes 0. Fine. If the one input of this NAND gate is 0, so here the output becomes, it is 0. So output becomes always 1. And if this 1 is given to here, then it becomes 0. Fine. So here the output becomes 0. So if the output is 0, then this state is called the reset. Means the output is reset to 0. Fine. So in the next case, what happened here? The clock is remains 1, it becomes 1, it becomes 0. This is the combination. So what happened here is the opposite. If S becomes 1, R becomes 0. So if the S becomes 1, R becomes 0. So here it becomes 1 and 0. So in 1 and 0, what is the output? Output becomes 1. Here the output becomes 0. And if the any inputs of this NAND gate is 0, so the output is here the 1, and this 1 and 1, here the output is 0. So here it becomes 1. So if the output is 1, Qn plus 1 is 1, then it becomes the set state, or we are saying this is our set state. So what is the next combination? So next combination is both S is 1 and the R is 1. What is the value in that case? So here we are saying S is 1 and the R is 1. So what happened in that case? So if both the inputs of this NAND gate becomes 0, 0, so what is the value in that case? In that case, we are saying this is invalid state. Fine, we already discussed this thing. This is invalid state. So we are saying this is invalid state or determined state. Fine. So this is the truth table of the SR flip-flop. Fine. So next is how to design this SR flip-flop with the help of our NOR latch. Fine. So what is the other difference between SR flip-flop and the SR latch? So in the SR latch, if we are designing the SR latch with NAND and the NOR gates, then it gives the two different truth tables. While the SR flip-flops, if we design it with the NAND latch, NOR latch, it gives the same truth tables. Fine. So the circuitry for SR flip-flops with the help of the NOR latch is this. So this is, NOR gate. This is second NOR gate. So in the SR latch, this is given here and this like this. Fine. So we are giving this thing with the help of the AND, and this is our clock, and this is S, and this is R. This is our clock. So this is Q bar and this is Q. Fine. So this is our SR flip-flops with the NOR latch. Fine. So this is our NOR latch. So if we evaluate the truth table of this SR flip-flops, then both these truth tables remains same. Fine. So next is the characteristic table. So basically the truth table and characteristics table are more or less same. While in the characteristics table, in the truth table we are representing the outputs and inputs. Here also we are representing the outputs and the inputs. But in the outputs we are representing both the states, previous states and the next state. Fine. So here the previous states I am representing as Qn and the next state is Qn plus 1. Okay. And here I am assuming our clock is always on, means the 1. Fine. So how many combinations here? So basically if we are saying here are the 3 inputs. So the present state may be 0 and the may be 1. So in the first combination both S and R is 0, 0. So this characteristics table can also be derived from its truth table. Here if S is 0, R is 0 and we are saying previous state is 0. So in that case what is the next state? So from the truth tables we know, from the truth table of the SR flip-flops, if S is 0, R is 0, then the next state, that is Qn plus 1, depends on the previous state, means it remains same as your previous state. So here also, here the previous state is 0, then the value of Qn plus 1 is 0 here. What happened in the next case? Next combination is 0, 0, and if the previous state converts to the 1, then what is the value of Qn plus 1? This is 1. So what is the next combination? This is 0, 1, 0. So if this is 0, 1, 0, then what is the value of the next state? Here the next state is, see, if both S is 0, R is 1, then it becomes reset, means the 0. Fine. So here Qn plus 1 becomes 0 here. Fine. And if this is 0, 1, and if this Qn is 1, then also it remains 0, means it is reset, it is Qn. Fine. In the next case, if it becomes S becomes 1, R becomes 0, it is 0, then it becomes 1, 1, 0, 1, it always 1. So all these Qn plus 1 values you can derive from the truth table of the SR flip-flop. Fine. So this is the set. What happens if S is 1, R is 1, Qn plus 1 is 0. So means the fourth state of our truth table, that is S is 1. See, this is our what? Invalid state here. Fine. So this is invalid state. So here also we represent this. If S is 1, R is 1, S is 1, S is 1, R is 1, then and Qn plus 1 is 1 times 0 and other times it becomes 1. So in both cases this is invalid state. Fine. So this is invalid. So this is the characteristic table of the SR flip-flop. So how to write the characteristic equation of this SR flip-flop? You already studied about the K-map. So here the output is Qn plus 1. So in the characteristic table we represent the output, that is Qn plus 1 as the function of the inputs. So if there are 3 inputs, then how many cells in the K-map? If there are 3 inputs, then 8 cell K-map. Fine. So first we design this K-map for this. So here I am saying S and here R Qn. Fine. So for K-map we need what? Characteristic equation. So what is the characteristic equation of this SR flip-flop? So the characteristic equation is means the representation of outputs in the form of inputs and the SOP form. So here the min terms are, which are the min terms? So this is 0, 1, 2, 3, 4, 5, 6, 7, right? So here's the output characteristic equation of this Qn plus 1. Qn plus 1 is basically the min terms is means the min terms is calculated when the output is 1. So here the Qn plus 1 is 1 at this first position and this fourth position and at this fifth position, and plus what? Don't care condition means this invalid state. Fine. So this invalid state is as 6 at the 7. So this is the characteristic equation. So from this characteristic equation we will write we will draw the K-map. Fine, to find the minimal solution of this. Fine. So here this is 0, this is 1, this is 0, 0, 0, 1, 1, 1, 1, 0. Fine. So this is 1, 0, 1, 2, 3, 4, 5, and this is don't care condition. Fine. So first we will solve this K-map. So this is what? This is possible or quad. Fine. So what is the value of this case? Here we assume both don't care are 1 and 1. So what is the value? Here the value is basically the S, and the second combination is this. So what is the value in this case? R Q N. Fine. So overall here the Qn plus 1 becomes the S plus R bar Qn. So this is the characteristic equation or the Boolean function for the SR flip-flop, S plus R bar Qn. Fine. So our next is, there is a one terms also that is called the excitation table. Excitation table. So excitation table is basically the inverse of the truth table. So in the excitation table, here the inputs are calculated from the outputs. So these excitation tables can be drawn from the characteristics table. So here's the, there are the two basically outputs, that is Qn plus 1 means the previous states and the next states, and the inputs are the S and the R. So if there are two here in the excitation tables, these are act as the inputs. So Qn and Qn plus 1. So based on the combination of Qn and Qn plus 1, we will calculate the S and R. So there are 4 possible combinations for Q and Qn plus 1. Both are 0 and the 0. So this is the case that both this is 0, 0 and this is 0, 0. This is only two possible case from the characteristics table. So what is the value of S in this case? S is both the 0 here. So this becomes 0. And what is the value of R here? One times it is 0 and the other times it is 1. So here I am saying this is the don't care. Fine. So next combination is Qn is 0 and Qn plus 1 is 1. So in which case this is here? This is first case. Fine. And the second case is only this is the possible case and the second case is this. But this is don't care. So this is invalid case. So what is the value of S and R? So here the S is 1 and R is 0. Fine. So next possible case is Qn is 1, Qn plus 1 is 0. So which case is here? This case. Fine. So here the S is 0, R is 1. And the next possible case is both Qn is 1 and Qn plus 1 is 1. So this is that case and the other is this case. So in both the cases R is 0, R is 0 and what about S? S is at one times it is 0 and the second times it is 1. So it becomes the don't care. This is the excitation table from the characteristic table. Fine. Here the input are Qn plus 1 and the output is S and the R. So from this excitation table we can draw the state diagram or the state transition diagram. So basically the state transition diagram is representation of the states or the whole working of the flip-flops is defined with the help of the state transition diagram. So you know that in the flip-flops there are two possible states, 0 and the 1, and how these states are changing as per the inputs. Fine. So basically here there are only two states, that is we are saying that is these two states, that is 0 and this is the 1. Fine. So this is Qn. So these are basically these two states, Qn and Qn plus 1. It may be 0, it may be 1. So that's why I am saying two states only, 1 and the 0. So what happens if Qn is 1 and the next state is Q also 1? So in which case 0 to 0? In which case when our S is 0 and the R is X. Fine. So what is the meaning of this? Means if the next state is also 0 and the previous state is also 0, in which case when S is 0 and the R is don't care condition. So next the present state is 0 and the next state is 1. So this case, this happens in which case when S is 1 and the R is 0. Fine. So next if the present state is 1, this 1 and the next state is 0, in which case this happens? This happens when S is 0 and the R is 1. Fine. So next if the present state is 1 and the next state is also 1. So this case. So this happens in which case? When S is don't care and R is 0. So this is basically the state diagram of the SR flip-flops. Fine. So next we will discuss about the JK flip-flop. Right. So tell me, what is the drawback of this SR flip-flops? Can you tell me? So from the excitation table, it is clear that this invalid state is basically the drawback of the SR flip-flops. When both the inputs S and R is 1 1, then the output is invalid. So to remove this drawback, we have to use the other flip-flops, that is the JK flip-flops. Now we will discuss the concept of two asynchronous inputs, that is preset and the clear in SR flip-flops. Right? So preset and clear inputs in SR flip-flop. Actually, what happens in the flip-flops at the initialization state means at the initialization we need to assign some particular values to the output means firstly we have to set or the reset the output so that these outputs can be fed back to the inputs and accordingly our flip-flop works. So for this purpose we need two asynchronous inputs named preset and the clear inputs. So why I am saying these two are asynchronous inputs, because these asynchronous inputs or these inputs, that is preset and clear, is independent on the other inputs, that is clock, S, R, J or K inputs. Fine. So that's why these are the asynchronous inputs, means independent on the clock used to operate the flip-flops, means the clock input given with the S and R inputs. So these two asynchronous are used to set or reset our flip-flop outputs. Fine. So now this is basically our SR flip-flops with output Q and the Q bar. If I connect these two inputs, these two asynchronous inputs, one I am saying this with this Nand latch, I am connecting two other inputs. This I am saying preset, and the second one is I am saying clear. Right? So now what happens here? First case is if this preset pin, right? This preset pin is 0. Then what happens? You know, in the NAND gate, if any input is 0, so if this input is 0 here, so if this input is 0 here, then what happens? That the output of this NAND gate becomes 1. That's why we are saying this is the preset, which means if this preset pin is 0, then it automatically set the outputs to 1. In this case, Q becomes 1 and Q bar becomes 0. In the other case, if clear is 0, if clear pin is 0, then what happens? If this clear pin is 0, then what happens? So if any inputs of this NAND gate is, if any input of this NAND gate is 0, then its output becomes 1 here. And if 1 is given here, then what is the value of Q? This Q becomes 0 here. Fine, and Q bar becomes 1. And that's why our output is clear. Fine, basically this concept is mainly used in the counters. When in the initialization states we need to reset or state in the up or the down counters. Fine. So this is the concept of preset and the clear pin. Now we will discuss now if I am saying this is preset pin, this is clear pin. What happens if both are 0, 0? If this preset is also 0, this clear is also 0. So both Q and Q bar becomes 1, which is not possible. So that's why this state or this condition is never used in the flip-flops. So never used. What happens if this P is 0, C is 1? Then our output becomes preset. Right? Means Q becomes 1. If this P is 1, C is 0, then Q becomes 0 or the clear state. Right? If both are 1, if both preset and clear pins are 1, means then it did not affect over the output. So if both this preset is also 1, and this clear is also 1. So these two pins now will not affect our outputs. So output not affected in this case. Fine. So what happens if preset is 0? Then only this pin becomes active. Fine. And if clear is 0, only in that case it becomes active. So that's why this preset and clear in SR flip-flops are active low pins. Right? Why active low pins? Because these pins becomes active when these values or 0 is assigned to these pins. Only in that case this becomes active. In some other flip-flops, these preset or clear pins are connected with the combination of some other gates. For example, in the D flip-flops. So in that case, this preset and clear operation can be done when 1 is assigned to these values. So in that case, these pins becomes our active high pins. Right? So active high pins means this pins becomes active when high value, that is 1, is assigned to these pins. So this is the concept of preset and clear inputs in SR flip-flops. So in the how to represent these pins in the form of block diagram. So this is our SR flip-flop. Fine. And in the SR flip-flops, we know one input is S, other input is R, and this is our clock. This clock may be level triggered or the S triggered. If I connect this, then it means the S triggers. And this is preset pins, and this is our clear pins. So why this round circle or why this cap? Because this is active low pins. Fine. And the output is Q, and here the Q bar. Fine. If I remove this bubble from here, fine, then this is now these pins act as the active high pins. Fine. So this is the difference between active high pins and the active low pins. Now we will discuss about the JK flip-flops. So what is the disadvantages of SR flip-flops? We already discussed. In the SR flip-flops, when both inputs S and R is 1, then the output is invalid states or the outputs are unpredictable. Right? So to remove this limitation or drawback, we have to use the next flip-flop, that is our JK flip-flop. So what is the difference between JK flip-flop and the SR flip-flop? So basically sometimes we are saying JK flip-flop is the extension of SR flip-flops. In the JK flip-flops, basically when the output of SR flip-flop is connected to the input. So in this case, this SR flip-flop is converted to the JK flip-flops. Now first we will discuss its circuit diagram of the JK flip-flop, then we will discuss its truth tables and the excitation tables. So we know the block diagram of SR flip-flop. So this is basically, this is clock, and this is S, and this is R, and this is, I am saying Q, and this is Q1. Right? So this is the block diagram of SR flip-flops. Now what happens if we connect these outputs to this AND gate inputs? If I place one AND gate here and the output, this is our Q bar. Basically I connect to the inputs here, and the other outputs Q is connect to the inputs of other. I connect this output Q to the input of other AND gate like this, then, and this becomes over, this input I am denoting as J, and this input I am denoting as K. Now this circuit diagrams or this block diagrams, now I am saying JK flip-flops. So sometimes JK flip-flops are also represented as, so this is what? This is basically what? Or SR flip-flops. Now if I connect the output, this Q bar here and this Q at the input of second NAND gate like here, now it becomes our JK flip-flop. Right? So truth table of both these circuits are same. Right? So now we will discuss it, the truth tables. So here, can you find the expression for the S? Here S is basically over J Q bar, and here R is basically K Q. Right? So now the truth tables of the JK flip-flop. So you know the truth table is basically the representation of inputs and the outputs. So you know here the input is over, first is clock, then the J, and third input is K, and the output is Qn plus 1. Fine. So now in the what is the first case if the clock input is 0. Fine. So if the clock is 0 here, then this output here becomes 1 and here becomes 1, and now if both inputs of the NAND latch is 1 1, then our output is remains as the previous states, that is our Qn, and this state is called the memory state, similar to the SR flip-flops. Now if I am saying clock is 1, and what is the first combination? When both J is 0 and K is 0. What happens in this case? If this J is 0, K is 0, then what happens here? What is the output of this AND gate? This here the output becomes 0 and here the output becomes 0. Fine. So you can also see from this other diagrams, if J is 0, K is 0, then what happens? This output becomes 1 and this becomes 1, and if the both inputs of our NAND latch is 1 1, then our output is remains in the previous state and it remains in Qn, and this is called the hold state. Right? So the third stage is if clock is 1 and J is 0 and K is 1. Right? So what happens in this state? So here I am saying J is 0 and K is 1. Fine. So here I am saying K is 1. So if the input J is 0, so output of this AND gate is 0 here, and here it becomes, basically here it depends on this Q. Fine. So initially if we are saying, so Q may be 0 or maybe 1. Fine. So if I am saying Q is 0, fine. So if Q is 0, it becomes 0, and if both inputs of S and R flip-flops is 0 0, and the output is basically remains in the previous states, and in the previous states here we assume this is 0, so output remains in this case 0. When I assume the next case 1, fine, if K is 1, fine, and Q is also 1, so here the output becomes 1, and if the inputs of SR flip-flops is 0 and the 1, then in that case output is 0. So always in both the cases when Q is 0 and Q is 1, or Qn plus 1 remains in 0. So this is called the basically reset state. Fine. So in the next state, if I am saying clock is 1, J is 1 and K is 0, opposition of the previous states. Fine. So what happens in this case? If I am saying J1 here and K0 here, fine, if I am saying K0 here, so here the output becomes 1. Fine. So in the next state, if clock is 1, J is 1, K is 0. Here J is 1 now and K is 0. If K is 0, then output of this AND gate is independent on the second input on Q, and here the output becomes 0. Here if J is equal to the 1, now here the output of this AND gate is depends on this second input, on this input. So if this input may be 0 or may be 1 because this is connected to the Q bar. Fine. So if I am assuming this is 0, and in that case output becomes 0, and if the both the inputs of S and R is 0 0, so in that case our output is remains in the previous state. So in the previous states here Q is 1 and Q bar is 0. Fine. So if I am assuming 1 here, fine, and the output becomes 1, and if the inputs of SR flip-flop is 1 and 0, so in that case output is always 1. Fine. So in both these cases, so the output is 1 and this state is called the set state. And in the next case, if clock is 1 and J is 1 and K is 1, so what happens in this state? If I am saying J is 1 here, fine, and K is also 1 here, fine, so what happens? It depends only on this Q, and here it depends on the Q bar, fine. So if the Q bar is 0 1, and then Q bar must be 1 0, fine. So if it is 0, Q bar is 0, in that case this output becomes 0 here, and if this is 1 and this is 1 here, output becomes 1. So in that case, if both inputs of SR flip-flops is 0 and the 1, in that case our output becomes 0, or output becomes means Q becomes 0 here and Q bar becomes 1 here. If Q is 0, in the previous states we assumed this Q is 1, fine. So the output Qn plus 1 is the inverse of the previous state, and we are saying this state is over the toggle state, fine. So in the JK flip-flops, when J and K is 0 0, in that state is called the hold state. When J is equal to 0, K equal to 1, output is always remains 0, that is the reset state. If J equal to 1, K equal to 0, output always remains 1, it is called the set state. If both J and K equal to 1 1, then the output Qn plus 1 next state is equal to the inverse of the previous state, fine, and that state is called the toggle state here. Now we will derive the characteristic table from this truth table, fine. So here the characteristic table of JK flip-flop. So in the characteristic table, you know the inputs are basically over the J, K and the Qn, and here the output is Qn plus 1. So this characteristic table can be easily derived from its truth table. So what is the first case? If J equal to 0, K equal to 0 and Qn means the previous state is 0. So what happens in this case? J equal to 0 here, K equal to 0 here, output is the previous states, and here the previous state is basically 0. So here I am writing the 0. If our previous state is 1, that is the Qn, then the next state becomes the 1. So this is basically our Qn. So what happens if J is 0, K is 1 and our previous state is 0? So basically this case, J is 0, K equal to 1, in that case output remains reset state, means always remains 0. What happens if the previous state is 1 like this? It also remains 0 in this state also. So this is over the, or we can say the reset state, right? And in the reset state, what happens in the next case? If J equal to 1, K equal to 0 and the previous state is 0. So this case basically, right? So in this case what happens? Output Qn plus 1 is always set, means the 1. So here I am writing 1. So this output Qn plus 1 also remains in 1 when the previous state changes to 1 here, fine. So 1 0 1, also in this case the Qn plus 1 remains in the 1 state, and this is called the set state. What happens in the next case when J is 1, K equal to the 1? So the last state of the truth table, when J equal to the 1, K equal to the 1, then the next state is basically the inverse of the previous states. Here if I am assuming previous state is 0. So what is the value of the next state here? 1. Inverse of this. This is the 1 as per this truth tables. Now, if j equal to the 1, k equal to the 1, now the previous state is changed to the 1. From the next state it becomes the 0. So this becomes basically Qn bar, and this state is called basically the toggle state. So this is the characteristic table of our JK flip-flops. Here this is 0 basically, this is 1, this is 2, 3, 4, 5, 6, 7, simple octal number representation, start from 0, 0, 0 to 1, 1, 1. Fine. So now, what is the characteristic equation for Qn plus 1 in terms of min terms or don't care condition? So, you know the min terms are defined when the output is 1. So, here how many min terms? 1 and 2, 3, 4. So, 4 min terms. So, min terms are represented as sigma m, and the min terms at position 1, fine, and min terms at position 4, min terms at position 5, min terms at position 6. So this is the characteristic equation of the JK flip-flop. So how to minimize this expression, or how to write the Boolean expression for this? So for this we have to draw the K-map first. So here how many variables in the input? So 3 variables. So how many cells? 8 cells K-map. Fine. So I am saying this is our 8 cell K-map, and here I am saying J, and here K, Qn, and this is 0, 0, 0, 1, 1, 1, and the 1, 0, and this is the 0 and the 1. Now I am writing. So which cell is 1? 0, 1, 2, 3, 4, 5, and the 6. Fine. Now, how the combination takes place, how the pairing takes place? One pair is this, fine, and the other pair is this, and this pair. What is the output of this pair? So the output of this pair is K bar Qn, and the output of this pair is basically the common is Qn, and the output of this pair is basically the Qn and the J, right? J, Qn bar basically. Here this is 0, so that's why Qn bar J. So here the Qn plus 1 is represented as J, Qn bar plus K bar Qn. So this is the Boolean equation for our JK flip-flop, right? Which you have to remember. So now, what is the next? Next, we will discuss the excitation table of our JK flip-flop. You know, the excitation table is completely the inverse of the truth table. So in the excitation table, you know, the output becomes the input and the input becomes the output. So here the inputs are Qn, Qn plus 1, and the output is J and the K. So this becomes the input here, and this becomes the output here. Fine. So what happens here? So how many combinations for this Qn, Qn plus 1? 4 combinations: 0, 0, 0, 1, 1, 0, and the 1, 1. Fine. So if both Qn and Qn plus 1 is 0, 0, so basically this one case and this other case. Fine. So what happens in both these cases? Here J is 0, J is 0, and what happens K? In the first case, K is 0 here, and here K is 1. So I am writing here K is our don't care condition. Fine. So what happened in the other case if Qn and Qn plus 1 is 0, 1? So basically this is this case, this one 0, 1 and the 0, 1. So what happens in this case? So basically 0, 1. So here's this one. Fine. So here's are J equal to the 1 always, and K is the don't care condition. So here I am saying J equal to the 1 and K is always don't care condition. What happens in the other case if Qn is 1, Qn is 1, this case, and q and bar is 0 here. Fine. Also this case 1 and 0 here. In both the cases, what is the value of j? J is basically 1. In one case it acts as 0 and the other case it acts as 1, and k becomes 1 always. So here's 1 and the don't care condition. Similarly, for 1 and 1, for this case 1 and 1 and this 1 and 1. So both for 1 and 1, here's the k is basically over 0 and j is the don't care condition. So basically this is the excitation table of our JK flip-flop. Now we will discuss the state diagram of our JK flip-flop. So in the state diagram is basically representation of the output states. So there are two states in the flip-flops, 0 and the 1. So if the previous state is 0 and the output is 0, means the next state is 0. In which case, means if the previous state is 0 and the next state is 0. In which case, when j is equal to 0 and k is the don't care condition. So what happens in the next state? If the previous state is 0 and the next state is 1, means this 0 to 1. In which case, when j is 1 and k is or don't care condition. What happens in the next state? The previous state is now 1 and the next state is 0. So this one. In which case, when j equal to don't care and k equal to the 1. Next state, when the previous state is 1 and the next state is also 1, like this case. In which case, when j equal to the don't care and k equal to the 0. So this is the state diagram of our JK flip-flops. Fine. So the home assignment for this JK flip-flop is you have to design a JK flip-flop using NOR latch. Fine. So students, if you have any doubt related to this topic, then you can send me a mail or you can contact me directly. So for more video update, please subscribe this channel. Fine, so that every information regarding your course or regarding this digital electronics lectures you can get easily. Fine. Thank you for your attention.